Hello everyone, and welcome to another episode of Coding Adventures. For many years I've been making various little simulations, graphics experiments, and so forth in the Unity engine. But a whole game engine often feels overkill for the kinds of stuff I'm doing. So for a while I've been toying with the idea of making a little lightweight rendering library of my own. Whether it pans out or not, I think there's a pretty high risk of learning some interesting things along the way. So let's see how it goes. Now, last year I coded a simple software rasterizer, which draws triangles one by one to an image on the CPU. And today we essentially want to hand that job over to the GPU instead, since drawing tons of triangles in parallel is pretty much its specialty. A lot of the maths we looked at then for transformations and perspective projection will come in handy again today though, so maybe have a look at that one if you missed it. Anyway, here are a handful of APIs I've been considering for communicating with the GPU. I started out tinkering with OpenGL and made this magnificent triangle before getting distracted by other projects for a couple of years. When I eventually returned though, I wanted to try something more modern and made a spinning monkey in WebGPU. But after some minor grievances with its shader language, me and my monkey moved to STL instead. I quite enjoyed using this, but for compatibility reasons I suppose some newer features aren't available, and in this project I think it'd be nice to have all the shiny toys at my disposal. So today I want to try starting afresh in Vulkan. Now normally I like to code in C#, but I think I'll write this library in C++, which I've only really used for little Arduino projects many years ago, but that way I don't have to worry about finding or generating bindings for every dependency I end up wanting to use. Alright, so I've got 4 things important to the project to begin with. There's the Vulkan headers to define the various types and functions available to us, along with 2 little Vulkan helpers called VMA and Vulk for memory allocations and loading of function pointers. And lastly, for now, GLFW for cross-platform window creation and input handling. Now, I've been learning the ropes from some guides like How to Vulkan in 2026 and a variety of Vulkan videos as well. The process does seem fairly involved, so I'll refrain from boring you with every single little step, but I just want to share the broad strokes as I go along this journey. We start off, unsurprisingly, by calling a bunch of initialization functions, and then use GLFW to create a window. By the way, I'm going to stuff various components, such as this window, into a structure called the engine, for want of a better word, just so we can reference them later. Then I've got this little run function here to test that out. So after creating the window, which enters a loop to keep it open until it's requested to close. And here's how that's looking. We can move the window around, resize it, sort of, and close, of course. Pretty snazzy. Even snazzier would be if we could actually draw on it though, so we'll need to get a hold of the GPU, but some machines might have multiple, like my laptop is with an integrated GPU and a more powerful discrete one. So this clunky code here gets a list of all the available ones, and then I'm simply picking the discrete kind if it exists. Now, we don't communicate with this physical device directly, but do so rather via a logical device created over here, which exposes a queue where we can submit commands for the GPU to execute. These commands need to be recorded into a command buffer, so I'm creating that here, and storing it as part of the window data, just so that if we want to have multiple windows open, they can each have their own set of commands. In fact, each window actually gets 2 command buffers here, because while the GPU is running the commands to render a frame, the CPU can already start writing the commands for the next frame, just obviously not to the same buffer the GPU is busy working with. That way, the CPU and GPU aren't always having to wait for the other to finish before they can start the next bit of work, and this is referred to here as having multiple frames in flight. Now, to manage these frames, or images that we'll be rendering to, we need to quickly create something called the swap chain, and this has some important settings such as the presentation mode, which determines when the image that the screen is displaying should be swapped out for a newly rendered one. Like, you can do it immediately and risk tearing, or wait for the next refresh cycle. I wrote a whole essay up here because I was a bit confused by the trade-offs at first, but I think it's making sense now. Anyway, after a few more setup steps, I've ended up with a window structure that looks like this, and most interesting here are these synchronization objects, allowing the GPU to wait first of all until a swap chain image is available to render to, and then once the rendering work is done, to signal that the image is ready for display. There's also a fence for it to signal completion to the CPU. Like, since we were using 2 frames in flight, we'd start off by creating commands for the first one and submit those to the GPU, after which we can imagine a fence up for that frame, meaning we shouldn't touch those commands anymore. But we can start work on the next frame already, creating and submitting commands for that, after which there'll be a fence up there as well. Hopefully by this point the first frame is finished rendering, but if not, the CPU will have to wait around doing nothing until the render is finally complete and sent off to be displayed, at which point we can imagine the fence disappearing, meaning we're free to write a new set of commands, submit those, and so the cycle continues. Alright, just whizzing through the relevant code quickly. That potential waiting is done at the start of each frame here, after which we request an image from the swap chain to render to, and reset the frame's command buffer so we can start recording new commands, such as those for a render pass. There we can specify what should happen to the previous contents of the image, and I'm just clearing it out with some background color. Then there's a bit of memory synchronization and other setup, but after that we're ready to start issuing commands we really care about, like drawing 3D models. But to check first that this is all working so far, I've quickly added an end of frame function, which basically just submits all the commands we've recorded, and asks that the image be displayed on screen once it's ready, and also increments our frame in flight index for the next frame. Here is the function for submitting the commands, by the way, where we pass in those various flags and fences. Okay, if you can believe it, that's all it takes to add some color to our window. Now, I've quickly hooked up an input callback to glfw so we're able to get keyboard events here. And I'm just noting on which frame each key was last pressed or released, so the state can then be queried whenever we want, like this. And to test that out, I made a little game of window pong. Wow, this is pretty intense. I guess we could make a lot of games just using loads of colored windows, but it's probably not the most efficient approach. So the next big goal is drawing some meshes. I've started out by defining a little vertex structure containing vectors for the position, normal, and UV coordinate, and these vector types are from a math library I've brought in called GLM. Then, keeping in mind that Vulkan treats -1 as the top left of the screen and +1 as the bottom right, I've created 3 vertices to form a triangle here. I've also got some indices to specify which points need to be joined to form the triangle, which feels a little silly when we have just one, but we want this to extend to much more elaborate meshes, of course. So from that information, I'm creating a mesh, which is a little structure I've set up here to hold this data both on the CPU side, as well as in GPU buffers for our shader to read from. Buffers are created by this function here, where that Vulkan memory helper is happily doing the heavy lifting for us. I'm just asking it to reserve some memory on the GPU, and then we can copy the given data into that space. This approach does have some system requirements, by the way, since traditionally the CPU can't actually touch most memory on the GPU, but it's very nice and easy, and we don't need to support every device in the world right now. Alright, it's time for our first super simple shader, which will be fed in vertex data over here, based on the buffers we give it. Right now I'm outputting the vertex position as is, just with an extra coordinate of 1, which we'll have a look at later. But these output positions are used behind the scenes to figure out which parts of the target image are covered by a triangle, and then this fragment shader here gets run on all those pixels, so we can say what color we want them to be. Here I've gone with the most creative color, green. This shader language is called slang, by the way, essentially identical to HLSL, which I usually use, but with some extra features that I haven't looked into yet. The shader needs to be compiled into something called SPEAR-V for Vulkan to understand though, so I'll drop in the slang compiler as another dependency to handle that for us. Okay, I'm running that over here on both the vertex and fragment stages, and the bytecode we get back needs to be handed over along with a bunch of extra info to create a graphics pipeline. That extra info is stuff like the layout of data in the vertex buffer, for example, or whether our triangles are clockwise or not, so it doesn't have to waste time drawing the backsides of them unless we specifically ask it to. But with that all set up, we are ready to draw. So on every frame we can call this draw function with our desired mesh and shader, and it then just records commands to use the associated pipeline and mesh buffers to do the drawing. And just like that, I've managed to make a whole bunch of error messages. But after wading through those, we have at last got a gorgeous green triangle on the screen. Such a momentous occasion must be celebrated, of course, so let's take a little break to just play around a bit in the shader. Like, I was flying to visit family recently and was inspired to write something by the view from the window. So I've scaled the triangle by a factor of 3 to fill the screen, and then normalized the current pixel coordinate to be between 0 and 1 in the fragment shader, before passing it along to a draw function to calculate the color of the world. Currently it just outputs the coordinate as a color, and here's what that looks like. But we'll need some randomness to create a terrain, so I'm now passing that into a function that just multiplies it by some big numbers and shuffles some bits around to give back a random seeming value. But that is of course too random for terrain, so we can clump the coordinates into bigger blocks, get random values for each of those, and then blend between them across space. And here's how that's looking at different scales. Now, terrain has got both small and large scale features, so we can simply sum up layers of the noise with various scales and weights to head in a more terrainy direction. Something like this, I suppose. But we're looking straight down at the ground right now, and I want a more out the window angle. So I've got some code here to calculate a point on the sort of image plane of an imagined camera based on the current coordinate and desired field of view, and that's then tilted up or down with a given pitch angle. Taking that, along with some view position up in the air, we can find out where the view intersects the ground plane, and use that location to evaluate the terrain noise. So I'll increase the angle here, and we can see a very speckly horizon line appear. I also play with the scale of the noise, and say everything above a certain threshold is land, and the rest is sea. Alright, after a few more tweaks, here's a little shape that I'm happy with. I'll just blend in some blues based on the noise values in the ocean, and do some more thresholding to add in a simple seashore. What I want next though are some little farm plots on the land. So I'm going to try using our noise function again to get a random farm value, but then floor it so that everything within a certain range becomes a single farm, for which we can then generate a random color to test it. Okay, these are quite the funky farms. I'll try playing with the scale, but it's not really looking how I imagined. Voronoi might be a better bet, so the idea here is to scatter random points around and then find the one closest to our current location. This can be done efficiently if we restrict the random points to 1 per square on a grid, because then we can limit our search to just a few squares surrounding the input location. With a mild trypophobia warning maybe, let's have a look at the shortest distance returned from here. And if I flip the colors around, we can see that these are like little bubbles that have expanded and squished up against each other. Using the closest point as a random seed, we can fill these out to form our farms, and apply it on the terrain with random colors. I think it's looking kind of interesting, but I'll show some restraint and limit it to just greens and browns. I'll also add a few small details quickly, such as slightly noisy outlines to the farms to represent rows of trees. Now, I think this needs some atmosphere, so using the distance to the ground plane, I'll make more light get lost the further it has to travel, since it can bounce away off the atmosphere atoms, to put it very crudely. And then the second part here approximates light that was traveling in some other direction, but then happened to bounce in towards the camera instead. I have a whole atmosphere episode if you're interested in more, but we can try losing some light, and gaining some light, and after a bit more tweaking, and a little tone mapping, I think that's looking much better. We're just lacking some fluffy little clouds to complete the scene. I have a video on that topic as well, but basically we can take tiny steps along the view array and evaluate some 3D noise to get the density of the clouds at each location. This lets us figure out how much light we'll be able to reach our camera from this point in the cloud, and with a little internal matching loop, also how much light from the sun we'll be able to actually get to that point in the first place. Combined, these give us a rough approximation of the total light we should be seeing. Depending on our particular parameters, that might be more or less accurate. At the moment I'm leaning towards probably less. But it's always fun to mess around and see how it behaves with various values. I think it's looking okay now, so I'll set the plane in motion, and we can watch the clouds and countryside pass by below. To animate this, by the way, I needed access to time, which shaders don't have by default, so that has to be sent over from the CPU. This can be done by creating a structure in the shader with all the information we want, and then an identical structure on the CPU to which the values are assigned. The data is then sent across with this little push constants command. We're only guaranteed 128 bytes of memory available for these pushes, so gotta keep it small, but it's a nice and easy approach. Anyway, now that we've tried one triangle, let's see if we can handle a whole 3D model. So I'm using a little library called tinyobj to load in mesh data from a given obj file, and then I've got a shader here that simply outputs the surface normal as the color. Alright, running this now on a world-renowned rabbit. It's a little too wide, upside down and missing both ears, but we all have days like that. So let's help it out. I'll start by tweaking some settings at the start of the render pass here, telling Vulkan that the window has a negative height so that the up direction becomes positive, like it obviously should be. Then to de-stretch the bunny, we just need to correct for the aspect ratio of the window, and I'm guessing the ears had Z values outside of the valid 0 to 1 depth range, so I've simply hard-coded the depth to 0 here for now. And with that, things are looking much better. But I want to admire the model from every angle, so let's spin it around. In the code, that just means taking the current time as an angle, and then getting a rotated version of the X, Y, and Z axes like so, and moving each coordinate of the input position along those new axes. Okay, that's looking good, but clearly there are some issues with the depth, which we can see even more dramatically if I disable backface culling for a moment. To solve this, we can give the GPU an extra image specially for storing the depth each time it draws a pixel, so that if another triangle ends up covering that same pixel, it can compare the new depth with the stored depth to determine which one should actually be displayed. This is configured as part of the pipeline creation for the shader, and the depth image itself is created over here. This will be used behind the scenes, we don't have to deal with it in the shader ourselves, but we do have to say what the depth actually is. So I've defined a minimum and maximum depth value over here, and remapped our bunny's z-coordinate to give us 0 at the min and 1 at the max. Let's see how that looks. Okay, I obviously need to shift it along the z-axis so it's actually within that depth range that I defined. And something else is strange. I think we're actually seeing through to the far side of the bunny, which means my triangles are the wrong way around. But after quickly fixing those issues, now I'd say it's looking good. This is a flat orthographic projection, however, so if we want a sense of perspective, we can take the xy coordinate here and divide it by z. That way when z is bigger, which is to say further away, those will end up smaller on the screen. Alternatively, we can get the same result in a weirder way by taking z and plopping it over here instead of the 1. That's because the GPU takes this fourth component and uses it to do the division for us behind the scenes. In fact, it also divides the depth, so we'd have to do a multiplication to counteract that. This is a slightly strange setup, but if you want to handle all the transformations with matrix multiplication, that final perspective division ends up being a sticking point. So having the division baked in as part of the pipeline is basically a workaround for that. Anyway, I want our bunny to have a bunch of babies, and we could draw them just with repeated calls to our draw function, of course, but there's some overhead to that, setting up the rendering state on the GPU, so if we're happy drawing them all with the same shader, there's actually a handy parameter in the draw call that lets us request multiple copies. We can then get the index of the current copy in the shader like so, and use that as a seed, for example, to generate stuff like random rotations, scales, and positions. So here's how it looks with 1,000 bunnies floating around in empty space. I know what you're thinking though, why are these bunnies not attracted to one another gravitationally? Don't worry, I'm on it. But it's not something that can feasibly be simulated in the vertex shader, so one option is to run the simulation on the CPU instead. Here's a little function to initialize a list of bunny data, just random positions, velocities, and sizes, with a mass determined by the size. That's then all used in the gravity function here to update velocity based on the attraction between a pair of bunnies, and here's some crude collision code to try prevent them from overlapping. These functions are being called over here, and because there's too much data to push to the shader like we've done before, the states are instead uploaded to a buffer. Now, we dealt with buffers earlier, but those were the vertex and index buffers which are used behind the scenes, whereas this time we want to access the data manually. The easiest way seems to be when creating the buffer, we can get the 8-byte address of where it's been allocated in memory, and then just push that little address to the shader. So it's stored in the shader here as a pointer to the instance data, and accessed using the current instance index. Alright, so with the data now read in from the simulation, our space bunnies should be much more realistic. This approach of calculating stuff on the CPU and then uploading the results each frame to the GPU for rendering is often a good solution. It's what most games do. But for large-scale simulations, it can sometimes be significantly faster to do everything on the GPU. In that case, though, we need a more general-purpose kind of shader, without all the bells and whistles of the graphics pipeline, where we can focus on the simulation side of things. And that is known as a compute shader. With these, we essentially ask for some function to get run, say, 1,000,000 times if we had 1,000,000 bunnies, and it'd do that more or less in parallel, giving us the index of each iteration, so we know which bunny we're working with. For example, I've got a simple test here which gets a bunny from the buffer using the current thread index, then moves it using its velocity and applies some kind of drag to reduce the velocity over time, before finally writing the updated state back into the buffer. One little detail though is that we need to specify the number of threads in a group, and I've gone with 64, which is usually a decent default. What this means is that imagine we had 65 bunnies in total. We'd need to run 2 groups of threads to cover all of them, though only 1 thread from the second group would actually be useful. The rest would be trying to work with bunnies that don't exist, so we should actually have a little bounds check to prevent them from modifying who knows what random memory. The actual purpose of these groups is something we can investigate another time, but on the CPU side, here's a function now for running the compute shader. And I've skipped over stuff like loading the shader and starting a compute pass, by the way, because it's all super similar to the rendering stuff we started with. But anyway, this function calculates the number of groups required to cover the total requested thread count, like we were just talking about, and then records the command to run the shader into our command buffer. Okay, let's try this out on 100,000 bunnies with random initial velocities. You might notice as they whiz past they're a bit more low poly now, because I have to reduce each one to about 1,000 triangles for the rendering to still run smoothly. But anyway, it seems like our compute shader is working nicely. For a more comprehensive test though, I've been working on porting over my old fluid simulation. This runs a whole bunch of compute shaders each frame, each with a particular task such as calculating pressure values, updating positions, and so on. Very little had to change in the shaders, just the way that the data is organized really. Like here's how it looks in the Unity version, where each of these is assigned from the CPU by name, and I just had to rework that to use our buffer address push constants approach instead. I made a few sloppy mistakes at first, like a mismatch between the simulation and rendering structures, but after fixing those, we can see our big block of fluid here inside the bounding box, and let's see how it flows. Alright, that's looking good, I'd say. Performance-wise, it's averaging around 500 frames per second, and I've quickly tried the same setup in Unity for comparison, and there it's averaging a little over 600 instead. So clearly I'm not doing things the most efficient way possible, but we're just starting out, and it's not too terrible either. Anyway, with both graphics and compute at least roughly working, I'd like to now make some bindings so I can try using this from C#. It would be a bit clunky though to just directly hand over the structures for buffers and shaders and so on, since they contain a bunch of internal Vulkan stuff. So I rather want the library to give out handles to these sorts of resources, which I've implemented simply as indices into a list of resources that the library now maintains. This did require an unfortunate amount of refactoring, but finally I've got a little API here where, for example, we can ask for a buffer to be created, and then use the handle from that to later upload data to the buffer, or look up some information about it, and so on for the other types as well. Alright, this is now compiled into a DLL, along with a horrible mess of dependencies that I hope to clean up at some stage, and then there's more thrilling code on the C# side to mirror the API over there. To make it more comfortable to work with, at least for how I'm used to working, I've then wrapped it all up in some objects like this GPU buffer here. That way we don't need to interact with the raw bindings directly, but can instead create a buffer with some initial values like this, and later update its values like this if we want, or get its address, and so on. Now, I want to port another project to test this out, and I think a good one would be the little text renderer I wrote some time ago. So I've brought that in, and here's how it's looking at the moment. The idea with this is to draw a quad mesh for each glyph in the text, and upload the font's Bezier curves to a buffer so that the shader can run intersection tests to determine if the current pixel is inside or outside of each shape. Pixels on the outside should be transparent, but that's evidently not supported at the moment. So I've had to trudge back over to the C++ side and update the API to provide an option for alpha blending when creating a shader, which then sets the appropriate flag over on the pipeline. I imagine there'll be a lot of this back and forth at first, filling in many missing pieces. But now the text is working. So I've been setting up a slightly fancier test next with our beautiful bunny back in the scene, and some information about it from Wikipedia on the side, just for fun. I also made an extremely crude UI system, simply drawing some quads to create this little settings panel where we can control the speed the model should spin at, as well as its scale. I haven't actually tested negative scales yet though. It's looking a little cursed currently. By the way, I might switch to a library like GRIMGUI for the UI later, but I'm happy with the setup for now. Anyway, over here we also have a next button, which allows us to crash the program, though only about 50% of the time, so it's a pretty exciting gamble. I eventually tracked this issue down to the text renderer requesting a bigger buffer, which meant my library was releasing the old one while the GPU was potentially still using it for rendering the previous frame. So to fix that, old buffers are now queued up to be released a few frames later. I also realized then that I don't have anything to prevent data uploaded to the buffers from overwriting values currently in use for rendering. So my clumsy solution for now is to manually flag if a buffer is intended to be updated each frame from the CPU, and then the library internally allocates separate buffers to switch between for each frame in flight. Anyway, going back to the test, pressing next is a lot less suspenseful now. It just takes us reliably to a teapot, which I'm noticing has actually got a bit of a wobble. I think this version must be slightly off-center. Maybe I'll fix that at some point, but for now, let's go next again to visit the Stanford Dragon, say hello to Suzanne the Blender Monkey, and lastly, a famous little boat. Now, obviously there is still so much stuff that I want to implement and improve and tidy up, but I think for a version 0 of the library, we've made a pretty good start here today. My understanding of all the synchronization stuff is a little questionable at the moment, so that is one aspect I'll need to study, but I definitely can see myself tinkering with this more in the future. So let me know if you'd be interested in seeing videos about that, or if this was so dull you've long since drifted off to sleep, then sweet dreams, I suppose.